Hello class, this is Ms. Riggins with today's video on section 5.4, Theorems About Definite Integrals. As you're watching the video, please remember to write down important theorems, statements, equations, examples, or graphs. Feel free to pause, rewind, or replay the video as often as you need so that you can get a clear understanding. And at the conclusion of watching the video, write down a brief summary about what went on in the video in your notes and submit that summary as well as a top question via the online whisk the day before class, ideally. All right, let's begin. Today we are going to be looking at some theorems about definite integrals. We've talked about in the previous videos different ways to calculate the definite integral or to look at the definite integral, but then we're going to talk about ways today on how to use the definite integral in a variety of ways. Let's begin. So actually, these two properties from Theorem 5.2 involve having some constant values, a, b, and c being any numbers, and f being a continuous function. And this first property basically says that if the definite integral from b to a is going to be the same value as the definite integral from a to b, except the sign is going to be different. Okay, so it basically talks about the area under the curve is going to be a different value if we're going from b to a than it is from a to b. So, and the second property we're going to take a look at is if I have, instead of an interval from a to b, if I have an interval including c, I can break up that interval in such a way. So really by basically adding up the areas under the curve. And how do I do that? Well, the proof is, and we're going to just do the word statements. The first one says that the integral from b to a is the negative, oops, I can't draw a straight line, of the integral from a to b. That's all that this says. And then the second statement says that the integral from a to c plus the integral from c to b is equal to the integral from a to b. Now, it doesn't specify the relationship between a, b, and c, where one is bigger, one is larger, one is smaller, but this will hold no matter what the relationship is. So to get an understanding of why that's the case, I'm going to basically talk you through an explanation, not a proof. When you get into analysis in college, then you will do a more formal proof. But since this is beginning calculus, we won't do a formal proof, just an explanation of why that works. So we have an understanding of why it works. And the reason why it works is kind of obvious. If we were going to look at this in the case of this example, this situation, it's really all about position. If you remember, if f represents a velocity function, then the definite integral will represent the total distance traveled. So if the total distance traveled from a to b is a positive value, then the total distance traveled from b to a would be a negative value, and vice versa. So that's how I can explain that case. All we're doing in this case is changing where we start at and where we end at. So therefore the sign is going to be different even though the values are going to be the exact same. To explain the second part of the theorem, it's going to be all about that area. All about that area. Okay, so anyway, so of course I said A, B, and C. We don't know the relationship between the two, but let's just assume that A is less than B, okay? Let's just assume that, okay? And we're going to take a look at two examples. So in this case, let's say f is a function above the x-axis. And here in this case, c is between a and b. And as we can see that the area from a to b under the function can be broken up into the area from a to c to the area from b to c. Oops, different color. If c is between a and b. But what if c is is bigger than b? Okay, so the area from a to b is still, but in this case now, the area from a to b is just this piece right here. And the way I compute this is to first of all evaluate the area from a to c, which is all of this, and then add the area from b to c, which is this piece right here. Oops, I'm going to do the same color. But one of the things you should know is this is from B to C. So in this case, we can use number 1 to switch that out because this is from B to C. So B should be down here and C should be here. So really this is a result of subtracting from C to B. And then we'll get what's left over is this. Okay, all right. Moving on. Let's go to the next page. Properties of sums and constant multiples of the integrand. So let's say I have two functions, f and g, that are continuous on the interval, and let c be a constant. Well, one of the things is if I want to take the definite integral of the summation of two functions over the definite integral, I can do that by taking the definite integral of the one function and add it to the definite integral of the second function. And that works as well. Same thing here. If I have the product scalar multiple of a function, I can find the area under the curve of that by taking that scalar multiple c and multiplying it times the area under the curve of just the function. And the way we can explain that is essentially the same thing, but in this case, instead of being about area and the like, it's all about summation and area, but it's also all about summation. So if you recall, the definite integral can be found by taking the summation of the function values at different subinterval points and finding the limit as those number of subintervals goes to infinity. But basically using the property of algebra and summation, this expression here can be distributed to look something like this. So when we try and find the sum of all of these intervals, we basically are finding the definite integral for f from a to b plus the definite integral for g from a to b. And here's a picture that kind of explains that as well. So as we can see here, from a to b, this is f. And then from a to b, this is g. So the whole thing can be found by basically finding the area from here to here. But some of you may be saying, well, isn't the function of g going to be bigger than f? Well, it could vary depending on the situation. So in this example, I just used that we add g to f instead of adding f to g. Okay, so it still works. So it's good that you remember that relationship as well in this case. So let's look at an example. How can we evaluate this definite integral? To make life so much easier, let's try and simplify this problem. And we simplify the problem by using the two properties we've been looking at. First of all, let's break up this into two definite integrals. And so what we do is we say, okay, this plus this, okay? And then I'm going to use the fact that this is a scalar multiple and pull out that 3, okay? And so we end up with something like this. Well, let's take a look at this concept, because this right here, if I were to look at this as a function, this is the constant function. So the area under the constant function of an interval looks like a rectangle. And this right here is a slanted function, so the area under the curve from a to b looks like a triangle, and we multiply that area by 3. So in this case, using an example, the reason why I ended up with 8 is the area of this rectangle right here is 2, because we're going from 0 to 2, and the height is 1. And the area of this triangle can be found by 1/2 base, which is 2, times the height, which we could see is, what was the height? Oh yeah, 2, and then divided by 2. So we get an area here of 2 and an area here of 2, but we multiply that triangle area by 3. Okay, and we get that. Simple enough. And the last thing we're going to take a look at is the area between curves. If I have two curves on an interval and I want to find the area that they make in between them, then basically all I have to find is the definite integral of the difference of these two functions on this interval. And the best way to use that as an example is this lovely picture. In this case, f and g are above the x-axis, but which makes life a lot easier. So what I'm going to do is the area under the curve of f of x, and here's my f of x, can be determined using this yellow. Sorry, I can't draw that well. And the area under the curve of g of x, I don't know if I want to do green. Let me try blue. Sorry. Looks like this. Because this is it ends up being green, huh? Yeah. And so the difference between the two would be this area right here, this little oval area. Okay, so to compute that, I would just compute the area under the curve of f of x and subtract it from the area under the curve of g of x. So that would be the definite integral using this expression. That's how I would do that. And the last thing is we're going to use symmetry to evaluate integrals. So remember, even functions are symmetric about the x-axis, and odd functions are symmetric about the origin. So if I have the limits of integration not being two different values, a and b, but letting a and negative a, i.e. they're on opposite sides of the vertical axis, then I can basically describe the area by multiplying the area from 0 to a instead of times 2 to be able to get the answer. And in this case, since g is odd, then the sum of the areas from negative a to a would be 0, since the graph is symmetric about the origin. So a good example, good understanding is the picture here. This is an even function, so if I want to find the area from negative a to a, then basically a shortcut way is to find the area from 0 to a using the definite integral and multiply that by 2, and we'll get that. And then over here, because f is an odd function, then to find the area from between negative a and a would basically be 0 because they are exact opposite values. Same values, but different signs, and so they cancel each other out. All right, this video was a little bit longer than I planned, but I hope you're able to understand me talking through this example. Thanks.